Okay, so my first task here is to talk about methodology and protocols for building models known as quantitative structure-activity relationship modeling. As you will see, it will build on what you already heard. And the progression that I'd walk you through is from data to models to molecular discovery. So that is the overarching objective. So to introduce the objectives of the exercise, what we want to do is to explore existing data on chemical structure activity relationships, empirical data, process this data, and enable the identification of new molecules expected to possess specific biological activity. So the overarching protocol is shown in this diagram. And the process that I will walk you through starts by identifying an empirical data set that has been collected experimentally, where chemical structures have been tested against certain targets, and empirical data on biological activities of chemicals have been collected. So that's reflected on the top of this diagram. In order to enable computational processing of the data, we need to transform chemical structures into chemical descriptors, establish the transformation of measured properties or activities into categories or real numbers, and then employ various protocols that are relying on statistical or machine learning techniques in order to generate models. And these models are then used typically for virtual screening of ever-growing chemical databases of untested compounds to nominate molecules expected to be biologically active or predicted to be inactive. This overarching protocol is used in multiple areas of research. We published a review a couple of years ago called QSAR Without Borders, and that essentially captures various types of applications of the tool. Something to emphasize is, and that's really has been what I would describe as a big bang of the chemical universe, the source of new molecules comes from untested chemical compounds. Those have to be explicitly described in terms of their chemical structure and enumerated. And it's been an enormous growth in the size of the databases. Up to about 2 years ago, the max we could get would be up to 1 billion compounds explicitly enumerated with known chemical structures, virtually enumerated. In the last couple of years, companies such as Enamine in Kyiv made available about 37 billion molecules that they have enumerated. They're synthetically feasible. The empirical success rate of the synthesis is about 80%. And then another company called eMolecules recently announced the availability of more than 7 trillion compounds. So those are chemicals accessible for potential exploration in the virtual screening library. What is important for this field is how we represent molecules. And so what is unique to cheminformatics is the representation of compounds by so-called chemical descriptors. And I'd like to emphasize this because people who study theoretical chemistry typically are exposed to various ways of representing chemicals that then is used for different type of computing. So in most theoretical courses, quantum mechanics is used, and there is an appropriate representation of chemicals in terms of electron matter and distribution of electronic structure. In molecular mechanics, we use a simplified representation of molecules, and this is also quite familiar to people in molecular simulations. In cheminformatics, the uniqueness of the field is the representation of molecules in the form of numerical descriptors, and that is what enables the use of machine learning techniques. So the representation and computational tools are tightly linked, and that's the point I want to emphasize. You just heard a lecture on graphs. So graphs have been borrowed from mathematical theory of graphs by chemists and really enabled the development of cheminformatics and various cheminformatics tools. And there are different ways of representing molecules. The simplest, which sometimes is confused with descriptors, is so-called smiles that I imagine most people in the room are familiar with. Smiles have been historically used to capture in a compact form the image of a chemical reflecting chemical connectivity and composition of molecules. Interestingly enough, in recent years, this representation has been used to transform smiles into a form of descriptors by molecular embedding, and I'll mention this toward the end. Most frequently, the compounds have been represented by transforming chemical drawing into a chemical graph or molecular graph, where atoms would become vertices and edges of the graph would represent bonds. And those would be labeled unidirectional graphs that can then be used to produce multiple chemical descriptors. If we capture three-dimensional information about molecules, then we calculate so-called three-dimensional descriptors. Those are reflective of the three-dimensional structure of the molecule. And so according to the representation, people have elaborated on 1D QSAR, 2D QSAR, 3D QSAR, and if in some cases molecular dynamic simulations are used to simulate the motion and conformational modification of chemicals, those have been referred to 4D QSAR, etc. So this is sort of the basic information. It's important for this type of tool and for understanding how chemical structures can be used in combination with machine learning techniques that chemical descriptors afford the transformation of chemical structure into machine learning ready format, and as illustrated on this slide. And if we collect the data and transform chemical structures into multiple chemical descriptors, then we get a data matrix. And in terms of the objective of the analysis, we identify empirical properties associated with chemicals that can be collected or computed, global molecular properties, and then individual descriptors could be regarded as variables or features or variables in the context of machine learning representation. So then, from this type of representation of data sets, one could derive models and essentially employ data matrices and recognize that the target property, a single or multiple target properties, can be computed from the matrix representation of chemical structures in the form of multiple chemical descriptors. So essentially, at this point, we get to employ essentially any machine learning tool that could take this input matrix of chemicals represented by their features and contemplate an empirical question of what type of transformation of these features could result in the calculation of target molecular properties, which could be biological activities or physical properties such as solubility, etc. So that's sort of the starting point. I think you've heard about the majority of machine learning techniques, and essentially this field had benefited progressively from any statistical machine learning techniques introduced in general in the field of statistics or machine learning. Just to recoup a couple of the frequently used representations among nonlinear methods, one that has been popular in the field has been K nearest neighbor, just as an example, where we sample features in any given data set and employ variable selection protocols to improve the fitness between molecular features and the target properties. And it's a very simple nearest neighbor based method where biological activity of a new chemical is predicted from that of its nearest neighbors. And those nearest neighbors could be identified in the complete set of features or a subset of features. So in the latter case, we employ multiple different types of statistical sampling of features to optimize the selection of features that maximize the agreement between actual and calculated biological activity. And then more complex methods, such as support vector machines, have been introduced where through a process known as featureization, transformation of the original descriptor into feature space, one is trying to develop a linear function that would discriminate between classes of compounds that would enable the calculation of the real value associated with molecular properties or molecular bioactivities. So essentially, any machine learning technique, again, can be used for as long as the original data is represented in the matrix format, and that's a very natural representation of any chemical data set, as I showed earlier. What I want to emphasize is not how to build models. That can be executed once the chemical structures are transformed into chemical descriptors, and there are multiple commercial and non-commercial software packages that enable this transformation and calculation of individual molecular descriptors. What is not as easy to capture, especially when people come from statistical field or non-statistical field, is the idea of the model validation and protocols and important critical data and model transformation operations that assure the external predictive power of the model. And that aspect is not necessarily well understood because in many cases of statistical data exploration, there is an underlying concept of sampling from a restricted, overall restricted space of features. In chemistry, and that's something I could have emphasized in the first slide, the chemical space essentially is unlimited. I've mentioned how the accessible chemical space has grown over the years and now reached dozens and hundreds of billions of molecules. And so there is no such thing as a restricted, by default, chemistry space. And so in that regard, we absolutely have to recognize that every time we build a model for any particular data set, when we try to make predictions for external molecules, we effectively always have to extrapolate in the unlimited chemical space. And that means that we need to worry a lot about protocols for model validation, much more than we worry about protocols for model building. Those have been established and continue to be developed, and those focus on how to increase the fitness to the data. But by default, do not worry about how to extrapolate beyond the training set size. And so it's critical to always think about how far you could extrapolate and how reliably you could extrapolate. And this whole field of extrapolation is still an active field of theoretical research in the field of QSAR modeling. So to this point, the protocols that have been developed by our and other groups emphasize the importance of testing model performance after building it on a training set, on a completely independent external set. Now, the latter is hard to come by unless you are a part of an ongoing drug discovery process working for a large academic group or a large corporation where constant synthesis and testing of new compounds is ongoing. So then we have to think about and choose protocols that would divide the existing data in some way to enable training and test set selection. And so that has been, continues to be an experimental empirical area of research in QSAR. And what is used most frequently, and we published several papers on best practices for model development and validation, and I emphasize validation, is that recognizing that all we have is the data at hand in the beginning of the process, all we can do is to set aside a fraction of the data and develop models using the remaining data. That set aside part can be done randomly, it can be done in some way of stratifying chemical structure diversity or maybe diversity of the biological response. And so our typical protocol involves taking the data set and dividing it in n equal parts, so that's n-fold external validation, and then developing models on the remaining subset of the data, employing concurrently different machine learning tools, building models, integrating models in the ensemble, and then using this ensemble to make predictions. So this protocol is outlined in a simplified form on the slide, and important to note that in no way can one use external data in order to optimize both the model and selection of models. When people develop training set models, you could have training set models of varying performance, developed with different tools with different subset of descriptors, and then you could then choose, or it will be highly attractive on the surface to choose models that make accurate predictions of the external set and claim that this models is what you want to use. And so that is, in fact, to be avoided. When we build and validate models internally, what we want is then to evaluate their performance on an external set. And if we fail in evaluating the performance, we have to essentially declare inability to build a successful model for a given data set. And that point is very important and often overlooked in even today in research publications. So what is important is not how to develop QSAR, it's how not to develop QSAR. And one of my colleagues years ago published a paper that's still highly contemporary today. And I give a reference here, and it's very important to read this reference, where he outlined, based on the analysis of models reported in the literature, 21 common errors that people make in developing models. And I outlined here a few of those that are not necessarily most important, but most illustrative, and that is undefined or ignored applicability domain of the model, and then also the point that relates to model validation. So applicability domain, another active area of research, and that is asking the question, given the distribution of the training set, in this case I'm using two-dimensional representation, how do we know if a new object can be extrapolated to or cannot be extrapolated to? And a new object is a new molecule for which we could calculate chemical descriptors, but the target properties are known. And so it's kind of intuitive that the principle of chemical similarity should be used. That is that if the molecule is within the training set distribution, then extrapolation is justified. If it's outside of the training set distribution, the extrapolation is not justified. So one of the common techniques in establishing the assignment of a new molecule to within or outside of the distribution is by the analysis of nearest neighbors of the new molecule. And so if nearest neighbors, if distances to the nearest neighbors in the training set are relatively small, the molecule is regarded as to be within the distribution. It's relatively large. The molecule is regarded outside of the distribution. And so this example on the left illustrates graphically how we could determine in or out of distribution, but you could also, and what we typically do is use a simple formula to detect in or out distribution that is based on the distribution of inter-compound distances in the training set. And so to establish this, it basically calculates the distribution of nearest neighbor distances in the training set, and then you ask for a new molecule if its distance to its nearest neighbors is within that distribution, defined by the mean and some number of standard deviations from the mean, or outside. Typically, when we employ this kind of restriction, we see that the molecules within the distribution have high accuracy of prediction. As you increase the applicability domain, you typically increase the coverage, so you could predict more compounds in the external set, but on average with lower accuracy. And so this kinds of considerations are pragmatic in that when you virtually screen an accessible, purchasable compound collections or otherwise gettable compound collections, depending on the tolerance of our colleagues conducting experiments and the amount of money that we have to purchase compounds, you could increase the applicability domain, you could increase the size of and the number of compounds you would test biologically, but you would also expect that the average accuracy of the prediction is going to go lower. If you could tolerate that, trying to capture more active molecules, then you increase the applicability domain. If what's important is the highest accuracy, then of course you make the applicability domain most conservative. Another aspect, especially for non-chemists, hard to recognize, is the aspect of data accuracy. We deal with empirical data. We deal with data collected from the databases. The initial belief and expectation is that the data comes accurate, and all we want to worry about is statistics. And that's completely wrong, because as we examine chemical structures of molecules in any databases or data sets accessible for modeling, we often find structural errors and often find bizarre values of the target biological activity or property associated with chemical structures. So perhaps you could see examples of molecules that any chemist would immediately recognize as improbable, to say the least. And nevertheless, that is a frequent observation in chemical data sets. And so the biggest time that we spend on developing models for new data is not model building per se. It's actually curation of the data. That's a very tedious process, and that is taken a lot of time, but it's at the same time as mandatory, and I will explain why. But generally speaking, and we've summarized the types of errors that we observe: structure inaccuracy, right? So that needs to be captured. Presence of misprints or wrong names. So there are two aspects to model building. One is structural accuracy. Second is the accuracy of measurements associated with the structure. And pretty much every practicing pharmacologist or biochemist know that data reproducibility is always an issue. And NIH years and years ago described this reproducibility crisis as something that haunts chemical genomics, molecular biology, etc. Sometimes you could see errors in descriptor calculation. Presence of duplicates is an enormous problem. People who test molecules typically don't care about the chemical structure. They care about having a substance that dissolves. And best case scenario, chemical structure cleanliness can be confirmed, but what they test is the powder or a liquid. They don't test chemical structures explicitly described by their connectivity. And so they give molecules different names. And so a typical data set would have large number of chemical duplicates that need to be detected prior to the analysis. Frequently, the size of the data is reduced dramatically. Our most dramatic experience has been with data on chemical toxicity associated with skin sensitization, where a data set that we've collected from the literature and electronic databases was reduced from 11,000 to 1,000, and that is not uncommon to see up to 90% data reduction. And I'll talk about why this is important. And then there are some special cases that need to be treated specially. If the data set has mixtures, it creates immediately multiple problems that can be dealt with but they need to be dealt with. And the problems include making a decision on what component of the mixture is a bioactive molecule. It's not always obvious. And if you have mixtures of 2 or more bioactive molecules tested at the same time, it creates an issue with how you validate models and how you look at the influence of the conservation of one of the components in of the mixture in the external set. So there are special protocols that need to be developed that deal with how you process mixtures and how you build models in those cases when mixtures are present in the data set. Similar considerations apply to salts, both organic and inorganic salts. So there are a lot of reasons to question the ability of building models if the data is wrong and if the protocols that we use are not validated. I'll use one example to illustrate the problem, which is not very obvious. And that's the example of nitro-aromatic compounds. Those of you who are chemists would recognize that this structures, the representation of structures on the right-hand side, all 5 are legitimate, all 5 from the chemical standpoint, but they're inconsistent. And as a result of inconsistency, when one calculates chemical descriptors that reflect compound structure in terms of not only number and connectivity of atoms, but the type of connectivities, single bonds versus double bonds, presence of charge versus lack of charge. So this inconsistency in the presentation leads to inconsistency of molecular descriptors, irreproducibility of model building exercise, different statistics of building, and a couple of examples that I illustrate here is that after normalization of nitro groups, in one case, the external accuracy of the model had grown from 0.5 to 0.9, in another case from 0 to 2.5. And this comes from empirical observations. So there are difficult cases that relate to a structure curation. Another aspect to remember, and people typically want to get model of the highest accuracy. When we curate the data, the result of curation could lead to seemingly lower accuracy of the models. It's not to be frightened. We're talking about empirically collected data. We're talking about trying to correlate chemical structure, which is the most objective way of characterizing molecules, and bizarre biological effects, especially in vivo, with unknown mechanisms and unknown elements of biological pathways. And so it's critical to realize that you should not expect to see models of 100% accuracy or 95% accuracy unless there are huge data sets, all measured following good laboratory practices. So known examples of models of extremely high accuracy is something like Ames genotox, or oral toxicity with thousands of compounds tested, where effectively almost any new molecule that is tested has a highly close chemical analog, and so you should expect high accuracy if the data is consistent and reproducible. Just to scare you more, nitro-aromatic case is a difficult one, but there are even more difficult cases with rare chemotypes where it's hard to detect slight differences between chemical structure of compounds. And so nevertheless, there are protocols that robust chemical structure standardizers would use to converge different structures onto the same chemotype. So those are sort of things not necessarily found in chemical textbooks or cheminformatics textbooks, and I wanted to bring this up. Why do we want to pay attention? Duplicates are unsafe for QSAR. It's kind of obvious, but has not been surprisingly recognized, especially in recent years. 2 or 3 years ago, I was attending conferences, listening to talks from people thinking they're doing an exceptional job using the most sophisticated computational algorithms on humongous data sets. And the title of the talk would be, Dirty Data is Great for Machine Learning or for Deep Learning. And that is that appears to be the case if your objective is to overtrain the model. But if we think about what happens when we use the models, we could train it on humongous data sets. But we're interested often, for multiple reasons, in accurately predicting small external data. And so overtraining the model on a large training set does not help to make accurate prediction for small external sets. And so what this slide emphasizes is that the difference between the primary objective of the model and primary objective of using models. And so in this regard, one could recognize that the presence of duplicates in the external set will undoubtedly increase the apparent accuracy of the models, because you essentially will be replicating the training set data in the test set. So emphasize the importance of very careful data curation. It is harder to deal with target property data because those have to be measured. It's under our control to curate chemical structures and harmonize chemical structures. It's not under our control to test or retest molecules. And so the only rational approach one could use is to look at chemically similar compounds, expecting that those should have similar target properties. And so what I'm showing here is an example of a data set where two molecules with identical chemical structures, both are from PubChem. And you know that they're identical without even looking at the chemical structure, although you always have to, because they have chemical ID the same, but substance ID different, because those substances were received from different manufacturers and purchased by substance ID, not by chemical ID. So the chemical identity was recognized. And as you look at the associated biological data, in this case, inhibition of various isozymes of CYP450, you find that one data point is inconsistent, highly inconsistent with the rest. And so for one of the major isozymes, the question is, it's about 3.5 orders of magnitude difference, right? So the question is, which of these numbers do you want to use for this molecule when we place it either in training or especially in the external set to validate the models? And a rational approach is to identify similar compounds in the same data set, look at the numbers, observe that these numbers match one of the two measurements, and kind of use this rationale in order to decide on what the accurate measurement associated with this compound should be. But that's, again, it's always a game, and we typically put these types of molecules in the external set and then use more reliable data to build the model and then make a decision on which one is more accurate by looking at the predictions, not only this kind of considerations. So there are published protocols for chemical and biological data curation, and I reference papers that describe those protocols and associated pieces of software here. And sort of last thing I want to expose you to is how to take claims and how important it is to be objective in both making claims and evaluating claims, especially when we are blinded by the excitement of new approaches, new tools, new methodologies. And so in chem informatics field, the excitement came when deep learning was introduced. And of course, everybody, immediately including our own lab, was absolutely fascinated by what can be done with large data sets effectively, and everybody expected that things will work. And so here is an example of an early excitement about the use of deep learning with a claim, which I cite here: deep learning methods significantly outperform all competing methods. The word significant is a very interesting one, and I'm very, very careful with the use of terms in the scientific literature, right? Because when you say significant other versus statistically significant result, you don't necessarily use any particular statistical test to call someone significant other. So it's really inappropriate to use, especially by a hardcore statistician, to use the term significant without actually justifying the use of this term by statistical validation. And so in this case, it's a colloquial use of term. And the reason I'm saying this is that if you look at the results more closely, and the results are comparing plain vanilla by today of methods such as SVM or random forest with an advanced neural net, right? And you say significant, but when you analyze actual data, what you find is that the numerical comparison of accuracy tells you that the best improvement is in 0.04 AUC units, whereas the variability across different modeling tools is an order of magnitude larger. So the error of prediction is an order of magnitude larger than the difference between the accuracy of one technique versus another. And there's no way in the world to call this significant improvement in the performance. And nevertheless, we use these words and blind ourselves and blind unprepared minds. Here is a more biological story. It was a paper published in Cell in 2020 claiming that using most advanced algorithm developed by our colleagues at MIT, they've managed to discover a broad-spectrum antibiotic that would kill every single bacteria on Earth. The most powerful ever discovered antibiotic on Earth, published in Cell. And the claim that was highly publicized was based on a paper published in a narrow professional journal, not Nature Science, Journal of Chemical Information and Modeling, introducing this technique, really elegant, really innovative, really interesting, captured a lot of citations right away, and basically said that this model could do miracles, develop statistically significant models. Again, in this case, the claim was justified statistically much better than the first case. If you look at the numbers, this is a version of deep learning. This is random forest using Morgan fingerprints, so very plain versus very sophisticated. And the numbers in parentheses are the numbers of improvement over random forest. And those, I would say, are significant. 20% plus minus a fraction of a percent is highly significant improvement, no doubt. And everything would have been great. Superb new method and superb discovery of novel antibiotic. But a few months later, in a much less cited paper, the authors said that they have made an error when processing random forest outcome. It's hard for me to understand why people who can develop really innovative deep learning approaches would misinterpret the results of random forest prediction, but that's what they did and admitted in a much less cited publication. And now things don't look as great. Now the same plain vanilla method works pretty much as well as the newly developed deep learning approach, right? Interesting observation. They continue, nevertheless, to say that the method works significantly better, which is not really great. But just to finish the story, it still would have been great because we have the world's most powerful antibiotic. But then Chemical Engineering News published a little unnoticeable line that says that the authors, they didn't retract the paper, but turned out that their colleagues working on the same floor at MIT had earlier identified the same molecule 3 years earlier, and it did have huge antibacterial activity as well as any cellular death activity. It basically was lysine the cell and was extremely toxic. They decided not to develop, not even to publish. They should have published. Bad result. So that sort of concludes this story. That story. The story generally continues during COVID, and I still really want to emphasize aspects that are non-technical, but it's important not only do upscale technical work, it's also important to properly evaluate this work. So I want to share this story too, and that is, there was a lot of excitement during COVID time about virtual screening and structure-based docking, and one of our colleagues even published a paper, How to Discover Antiviral Drugs Quickly. Discover antiviral drugs. That means FDA approved, right? No, it means that one could use the world's fastest supercomputer and run a lot of simulations and burn a lot of CPU hours and claim that there are a few molecules that actually bind to the main protease of the virus. Another colleague of ours, sort of commenting on papers like this, which I really loved, is discovery of new experiments is it really discovery of new incubators? So there is zero experimental data. Maybe it's best to use the term digital dream. And I strongly encourage you to be very objective in evaluating the results of the studies. We kind of commented on this in a recent feature in Chemical Society Reviews with a viewpoint called "Surely You're Joking, Mr. Dawkins." And that, of course, draws from Rachel Feynman's famous book and a fantastic quote that I found there, that people will redo experiments, and every time you publish something, think about those who will try to reproduce what you're trying to do. So AI methods, especially in cheminformatics, have been taken, should be taken very carefully, and the results should be analyzed very carefully. There have been publications talking about science crisis because new methods overpower training set analytics. I always suggest thinking about what AI means. If you search on the web what the word AI means, and there is a social science rule that if you want something to be memorized better, say it 3 times, so that the rule of three thumbs. If you say AI 3 times, Urban Dictionary says it's a phrase used by most evil people with bad intentions. Not necessarily as bad as I portray it, but when you do the most sophisticated algorithmic development, think about how to present it, how to use it, how to objectively evaluate the results of the study. So to be a little bit more optimistic, I've talked about traditional workflow for QSAR modeling, and I mentioned briefly in the beginning that typically we would calculate explicit chemical descriptors from chemical connectivity and chemical graphs. And would do virtual screening to select and test known molecules. In the last few years, multiple labs have started looking at, ways of embedding smiles using linguistic models and using generative models. So there have been workflows developed that would learn how to build new smiles, semantically attractive new smiles. And semantically attractive means that the new smiles that are generated correspond to chemically realistic molecules. And if you use QSAR methods or QSAR models to guide or to bias the generative models, then in the end, you get new chemical structures with novel chemical structures and the desired predicted activity. So this is a protocol that has been implemented in our lab in collaboration with my former associate, Ole Sisayev, who is at Carnegie Mellon, and that comes from a recently published Communications in Chemistry paper, where this protocol has been used to nominate and test new chemical entities against EGFR and one of the kinases, and we essentially succeeded in the end to identify new chemical structures that had, some of which had shown the desired biological activities. Not all, but some. And so that's where the field is going, is to employ deep learning as part of generative modeling in order to generate compounds with new chemical structures, desired activity, and there is a lot of excitement in this area. So these are briefly the results of biological testing of new chemicals. So the field is going toward using models as part of automated chemistry and self-driving chemistry labs, and that is where I think a lot of excitement is in using QSAR models as part of the overarching data lifecycle and in situ implementation and use of models to guide chemical synthesis and process optimization. So there is a great paper by Alain Asper-Guzik that describes how this can be done, and he is building a huge, monstrous organization at the University of Toronto that really implements the self-driving labs context. So to finish, that's what we want to do. Establish curated SRA database, rationally divide the data set into training and test set, develop training set models, validate training set models, finally explore and exploit validated models for mechanistic interpretation and prediction. I'll skip this summary and just say that we all have to learn how to build models, because it's not that machines are going to replace chemists, it's that chemists who use machines will replace those who don't. And that comes from one of the blocks. So I do have an exercise, but I cannot run it because the system doesn't let me connect to Gmail, which is required. But I have provided a link, and with that link, there is a Python notebook that could be run for a data set of protein ligand complexes. So it's intentional uncommon data set from BindingDB, where proteins are represented simply by frequency of composing amino acid duplets. So it's an uncommon QSAR data set, and ligands are represented by traditional chemical fingerprints. And you could build a model that, so these are the principal component representation of both chemicals and protein structures by their compositional analysis. And if you run it, you get, depending on how you split the data, you get more or less accurate external prediction. So you could vary the result in R-square by simply changing the ratio of training and test set, or the number of divisions in the training and test set. And this is something that I intentionally didn't talk about. You could also get an extremely bad model. And you do that by using a process known as wire randomization, where you shuffle the labels associated with chemicals and repeat the entire model and protocol. Your expectation is that when you have random labels, then you get random model. And that is a very powerful internal accuracy, model accuracy test that I recommend to run always. It's not something, again, that is highly universally recommended, but that what you want to see is that the data that you have is non-random, and the method that you use does not overpower the data, essentially. So that's what wire randomization is about.